Okay, it's 7:30. Welcome to the November meeting of the Johnson Space Center Astronomical Society. I'm Doug Holland, the president of the JSCAS, and this is our agenda for this evening. If you have questions and comments that you would like to give to our speakers during the meeting tonight, you can send them at the email below, jscaslive@gmail.com, or you can enter them as a YouTube comment in the YouTube comments area if you have an account that will let you do that. So first on our agenda tonight, we're going to have Dr. Christopher Johns-Krull with Rice University on characterizing planets around other stars, the quest for life on other worlds. That'll be followed by David Haviland with a Members Minute on recent lunar images. Then I will be doing a DIY astronomy topic on remote control of radio telescope using Raspberry Pi. Then there will be a Members Minute by Chris Wells of recent images from the Eldorado Star Party. Then David Haviland will bring us Star Party news. And then we'll wrap it up with Treavor Quinn doing a DIY astronomy Expedition Eldorado 2020. So for our main speaker tonight, I'd like to read you a little bit about Dr. Christopher Johns-Krull. Dr. Christopher Johns-Krull is in the Department of Physics and Astronomy at Rice University. There he has been an assistant professor, associate professor, and now professor since 2001. Prior to that, he was an assistant research physicist at Berkeley, a postdoc at the University of Colorado, and a W.J. McDonald Fellow at the McDonald Observatory at the University of Texas, Austin. He received his PhD and MA from the University of California, Berkeley, and his BS and BA from the University of Texas, Austin. His research interests are quite varied, but all are related to the astrophysics of lower mass stars, including the Sun. With that, I would like to turn it over to Dr. Christopher Johns-Krull.
Okay, well, thank you. Thank you very much for having me here today and for that very kind introduction. I really enjoy coming to talk to various astronomy societies, collections of amateur astronomers. That is how I got interested in astronomy. I grew up in Dallas and was a member of the Dallas Astronomical Society from the time that I was about 10 years old or so, and that's really what sparked my interest in astronomy and led me to pursuing it professionally. So I really enjoy talking to groups such as this because it was a group just like this that kind of got me launched on my career. So I'm going to talk to you today about some of the work that my students and I have been doing over the past several years and some collaborators at Lowell Observatory in Arizona. And I'll start off by showing you this image, which is sort of, maybe it would be seen as a strange sort of modern art piece if it was hanging on somebody's wall. It may not look particularly meaningful to many of you, but to me, it is quite a beautiful thing. And the thing that is so beautiful about it, in my mind, is this sort of whitish peak shown here in the upper middle part of it. And so I want to explain to you what this is and why I am so particularly excited about it. So we have to step back and set the stage for what we're doing here. And in general, I work in the area of star and planet formation. And our cartoon understanding of star formation and then ultimately planet formation is shown here on the left-hand side of this diagram. And so the first part is not to scale at all, but it is a cloud of interstellar gas and dust somewhere in our galaxy that becomes cold enough and dense enough such that the internal gravity of all the material in that cloud overcomes the pressure support from the temperature of the material. And the temperature is quite cold, on the order of, say, 30 degrees Kelvin. And this thing collapses under its own gravity, under its own weight. But because it's spinning, the thing that forms after this collapse is a central concentrated object in the middle, which will become the young star, the young sun, but there's a disk of material around it. And that's just due to the conservation of angular momentum The things that are on the farther outer parts of the cloud can't collapse all the way to the inside because they'll be spinning too fast, like the ice skater who pulls in their arms when they're doing a spin. They would be spinning too fast, they would be flung off. So they settle into an orbit that is some certain distance away from the central object, but everything can collapse along the rotation axis. There is no worry about conserving angular momentum along the rotation axis. So that naturally produces a disk-like structure. And it's in these disks that we believe the planets of our solar system form and the planets of other solar systems form. And that explains many things that we see in our own solar system. All the planets in our solar system basically orbit in more or less the same plane. That plane is pretty much the same as the equatorial plane of the sun. All the planets in the solar system are orbiting in the same direction. And all of these things can be very naturally explained by planets forming in a disk around a young star, around the young sun. But how that process actually happens is still debated and still not fully understood. We know that there are dust particles in these interstellar clouds before they collapse. Now, the dust particles are quite small, they're submicron in size. And so the disk that forms around these young stars should also have these dust particles. But because the disk has a range of temperatures very close to the newly formed star, the disk is maybe as hot as 1500, maybe even up to 2000 degrees Kelvin. But the very outer parts of the disk are quite cold. Again, only 10, 15, 20 degrees Kelvin. And so the volatile elements that are in the that may be in the disk everywhere get basically sublimated, evaporated from the very central parts of the disk, but they can survive in the outer parts of the disk. So you expect the inner parts of this disk to have what we consider rocky dust grains, so things like silicates and carbonate compounds and things like that. The outer part of the disk will have those same rocky type things, but it will also have small particles of water ice and methane ice and other types of ices that can form. And so the basic idea is that over the course of a few million years, maybe 10 million years, these small dust particles that are circulating around, orbiting around in this disk, they can collide with each other, they can stick together and gradually grow bigger and bigger things. And we call that general picture of planet formation the core accretion model. And if you were interested in finding a planet around the sun and you were on some other star looking at the sun, the first planet you could find, the first planet that would show itself is Jupiter. Jupiter is the most massive planet in our solar system. And this core accretion model, which is a very slow, gradual building up of things, suggests that it maybe takes about 10 million years to build Jupiter. But there's another competing theory called the gravitational instability model, which says actually that the disk itself is more massive than maybe we think it is. And it turns out it's actually quite hard to measure the mass of the disks around stars. And if that disk is massive enough, then you have to worry about the gravity associated with the material in the disk itself. And in that case, the disk can become unstable to its own gravity, and little pieces of the disk can collapse to form planets very quickly, kind of like pieces of our galaxy collapse to form stars. And so shown here in the upper right is a computer simulation of one of these gravitational instability models that shows a handful of planets forming in a disk in a very short time scale, maybe only 500,000 years. So where are all these planets and stars forming? They form throughout our galaxy, and they're forming now. And the Great Orion Nebula in the Sword of Orion is one of the nearest and richest regions of star formation. Here on the right is a Hubble Space Telescope picture of the Great Orion Nebula. And there are something on the order of 3,000 newly formed stars in the Orion Nebula. And when I mean newly formed, they are on the order of 1 to 2 million years old. And so if that core accretion model is correct, they shouldn't have any Jupiter mass planets If this gravitational instability model is correct, then maybe they have already started to form Jupiter mass planets. And so that kind of foreshadows some of the work that my team has been doing. We want to look for these young planets. Well, in terms of this whole idea of how planets form, the first thing you need is disks. Disks are very common. Disks are easily observed. The Hubble Space Telescope has taken some very spectacular pictures of disks around young stars. Shown here on the left is a collection of 4 stars where the disk happens to be edge on, oriented in such a way that it's actually blocking the light from the central star. The light you see above and below the dark lane in the middle is scattered light from the tenuous upper and lower layers of the disk, but you're not seeing the starlight directly. And on the right are some more pictures of disks, and this one here in the lower left of this right-hand section is kind of a nice example. This is a disk around a young star that is not edge on. The disk is this black thing, and you can see it as a black thing because it happens to be in the Orion Nebula, and it's in front of a lot of the nebulosity, and so it's absorbing the light from the nebula, and that's why it shows up as something dark. But if it was out in empty space, all you would see is the light from the central star. So because these disks are quite cold and relative to the stars, these are all pictures taken in the near infrared and optical by the Hubble Space Telescope. If the disk is not oriented particularly correctly, it's hard to see them in an image. But at radio wavelengths, and the Atacama Large Millimeter Array that is now operating in Chile, has been operating for several years now, studies the radio spectrum. This is the light that is produced by much colder things, and the disks themselves, even though they are quite a bit colder, emit substantially at the wavelengths of light that ALMA studies. And here are images of many disks around many stars that have been taken by this ALMA telescope. And so we see disks quite commonly. The formation of disks and that whole process of how planets form, that's well established, and pretty much 100% of stars, when they form with disks around them. So then the question is, how many of those stars form with planets around them? And so we need to work at finding planets. So how do we go about finding these planets? Well, one way to do it, and the way that the first planets around young stars were found, was through what we call this radial velocity method. And the radial velocity method, first, what you have to do is you take a spectrum of the star. So you pass the white light of the star's light through some device. A simple prism will do it. A prism will break the wavelengths of the light up into their different colors, and the different colors just correspond to different wavelengths of light. So red is longer wavelengths, blue is shorter wavelengths. And if you look at a spectrum of the sun through a prism in great detail, you will see these dark lines. These are what we call the absorption lines that come from the elements in the atmosphere of the star. So like these two dark lines here in the yellow part of the spectrum come from the element sodium. And one of these dark lines over here in the red comes from the element hydrogen. And then there are other lines from other elements. And if you blow up a particular region of the spectrum, say in the green here, you can look at the spectrum in much greater detail. These 3 strong lines that are shown in the top are from the element magnesium. But these other weaker lines that are shown throughout the spectrum come from other elements, and most of them come from iron. So a good trivia question: if somebody randomly points to a high resolution spectrum of the sun and asks you what spectral line is that, if you have no idea, you should guess iron, because iron is the element that produces the vast majority of the lines we see in the spectrum of the sun and other cool stars. So what we do then with these spectral lines is we look for them to move. So if you have a planet and a star, and you should be seeing the planet going around very quickly in this animation, when a planet and a star are in orbit, the star itself is moving. It's not that the star is stationary. It's the star and the planet both orbit the center of mass. The center of mass is the balance point between the star and the planet. So if you think about, a seesaw on a children's playground, if there's two people of about the same weight on either side of the seesaw, then the balance point is right in the middle, and you can both sit there and you will be equally balanced. But if you put a 300-pound NFL lineman on one side and your toddler on the other side, the balance point is not going to be in the middle. You're going to have to go much closer to that 300-pound lineman in order to reach a balance point. And that's what the center of mass is telling you. The center of mass of our solar system is a point in space that's just a little bit outside of the sun. So the sun itself is orbiting around the center of mass of the solar system. And because Jupiter is the most massive planet in the solar system, the sun is executing a primary orbit around the center of mass that has exactly the same period as Jupiter, and that's about 12 years. But because we have so many other planets in our solar system, the sun is doing this sort of intricate dance, this intricate wobble around the center of mass. But the majority of what it's doing is caused by the fact that Jupiter's there, and Jupiter's moving the sun around. So what we do is we just stare at stars for many, many nights over the course of, in some cases, many, many years, and we look for evidence that the star is moving. So what is that evidence? Well, that evidence is what we call the Doppler shift. The Doppler shift is what you may have experienced when you have heard the siren of a ambulance or police car, that it sounds higher pitched when it's coming towards you or lower pitched when it's moving away from you. And that's because the sound waves are being compressed as they come towards you. So the wavelength of the sound waves is actually getting shorter as the ambulance is coming towards you. And then as the ambulance moves away from you, the wavelength of those sound waves is actually getting longer, and that makes it sound lower pitch. The same thing happens with the wavelengths of light. As the star is moving towards us, all of these wavelengths of light get shifted to shorter wavelengths, so to the left in this diagram. And as the star is moving away from us, the wavelengths of light get shifted to the right or to the red. So we look for these alternating blue shifts and red shifts as the star is moving, because there is some unseen companion, this planet, moving around in its orbit. And so the orbital period tells you something about how far away the planet is from the star, and the orbital speed, how fast that star is moving, tells you something about the mass of the planet. And that's how the very first planets were discovered around other stars. The very first one discovered is called 51 Pegasi. So in the constellation of Pegasus, it was discovered at an observatory in France. So this is a picture of that observatory. And shown here on the bottom left is the radial velocity measurements. So it's taking these wavelength shifts due to the Doppler effect and translating it into how fast would the star have to be moving to correspond to that shift. And to give you a ballpark figure, so the case of the sun going around the center of mass, because of Jupiter's orbit, the sun is moving at a speed of about 9 meters per second. And you can see.
Let me interrupt.
Sure, go ahead.
Sorry,
yeah.
We've got a question that's come in. The question was, I have read that we have not identified the elements that correspond to all the absorption lines. Can you comment on why they are still unidentified?
So that is true.
Lines?
There are some unidentified absorption lines. There are actually very few. We have identified most of them. And there's sort of two reasons for that. Atoms are complicated. Our basic understanding of atomic structure is quantum mechanics. And while quantum mechanics is a very well-established theory, a very well-established model, just the computational difficulty of doing an accurate calculation that describes what the predicted wavelength is for all of the possible spectral lines that a complicated atom, say like iron, could produce is a very difficult thing. Computationally, it's just very difficult. So from a theoretical standpoint, it is not possible to identify all of the spectral lines. And so then you need to be able to measure them in a laboratory. And so that means you need to prepare gases of known composition, so an iron gas that's at the temperature and pressure of the sun's outer layers. And then you need to do that for every element out there. And so it just takes time and effort, and it just hasn't all been done. So there are a few, but most of the lines in the sun's spectrum, for example, are well identified, but not every single one of them. So this, I was saying that the speed of the sun moving in its orbit due to Jupiter is about 9 meters per second. But the period of the sun caused by Jupiter's orbit would be about 12 years. So this 51 Pegasi, the star is moving not at 9 meters per second, but its amplitude is a little bit over 50 meters per second. So it's moving, more than 5 times faster than the sun would move because of Jupiter. But the orbital period is only on the order of 4.5 days. So if you work out all of Kepler's laws to figure out what that means that you have a planet around this star that is really, really, really close to its star. So Mercury has an orbital period of about 90 days. This is much, much closer to its star than Mercury. And the mass of the planet that would produce this type of signal would have to be about half the mass of Jupiter. So this is how this is the poster child. The first planet we discovered is the poster child of what we call a hot Jupiter. A hot Jupiter just means that it's really close to its star, that has an orbital period of less than about 10 days. And by Jupiter, we mean something that is approximately the mass of Jupiter. And in this case, this planet around 51 Pegasi is about half the mass of Jupiter. And just this past year, this discovery and the additional discoveries of extrasolar planets were rewarded with the Nobel Prize in Physics, and Michel Mayor and Didier Queloz are the 2 primary scientists, astronomers that discovered this planet 51 Pegasi, but they discovered many others. This is not the only one they discovered, but they really ushered in this field of exoplanet science. And I will say now we know of about 3,500 confirmed planets around other stars, including some very interesting ones. So for example, this on the left here now is the radial velocity signal of Proxima Centauri. So Proxima Centauri is part of the binary system of Alpha Centauri. These are the closest stars to the solar system. And these measurements and the line, the best fit line through here show you the radial velocity curve of Proxima Centauri. And instead of being an amplitude of 50 plus or minus 50 meters per second, this has an amplitude of only plus or minus 2 meters per second. So this is a much lower mass star, and it has an orbital period of about 10 days. Proxima Centauri itself is a very low mass star. It's an M-type star, a red dwarf, so it is much cooler than the sun. It's not emitting nearly as much light, and so it can't warm up the planets around it nearly as well as the sun can. And we know because the orbital period of this planet is so short that it must be relatively close to its star. And the low amplitude of it tells us that it's a relatively low mass. And when you work out all the details, this is roughly an Earth mass planet, a couple of times the mass of the Earth. But the exciting thing about it is that it's in the habitable zone around its star. It is close enough to its star such that the temperature is basically just right, so that if there is an atmosphere on this planet, liquid water could exist on the surface of the planet. And so that's what we mean by habitable, that liquid water could exist. Absolutely.
Can I interrupt you for a second? We have another question. What are the methods to discriminate the slight changes in the Doppler shifting of a star spectra to identify multiple planets orbiting a star?
So the way that would show up is, so this first one that I've shown here It looks like basically it's a single sine wave curve that describes it. If there were multiple planets, you would have a sine wave for the first planet, and then on top of that, you would have a sine wave with a different period for the second planet, and then maybe and then a sine wave with a different period for the third planet. So if you can think of taking sine waves of different periods and adding them together, that's what the radial velocity signal of a multi-planet system would look like. And that's the way you would try and find them, is by fitting multiple sine waves to the radial velocities that you see. And sine waves is cheating a little bit. Sine waves are only the right shape if the planet's orbit is perfectly circular. Most planets have a slight ellipticity to their orbit, and so they're not quite perfect sine waves, but they're close. But the mathematical shape of those functions is well known and can be fitted for. There's a second way to find planets, and that's what we call the transit method. And this is where we look to see if there are planets, if there are systems where the planet is at exactly the right orbital inclination so that the planet passes directly in front of the star, between the star and us. So if you think back to those pictures of disks around stars that I showed earlier from the Hubble Space Telescope, some of those disks were in the case where the disk was perfectly edge on or very close to being perfectly edge on. And those disks would form planets that would then pass between the star and the Earth. And so when the planet passes between the star and the Earth, if you just look at how bright the star is, when the planet goes in front of the star will get a little bit dimmer because the planet is blocking some of the light. And so what this tells you is really the size of the planet compared to the size of the star, because how much light it blocks depends only on the area of the planet compared to the area of the star, the projected area. And so again, in the case of the sun and Jupiter, if you happen to be on another star system looking at the sun and Jupiter passed between you and the sun, Jupiter would block about 1% of the light from the sun. So you would see the sun's brightness dim by about 1%. And that would happen every time that the planet went in front of the star. So if you were doing this for Jupiter, you'd have to wait 12 years for it to happen again. But if the planet is much closer to its star, then it can happen much more frequently. And in fact, we now know that that happens, that situation exists quite a bit. And that is primarily because of the NASA Kepler satellite, which is named after Johannes Kepler, who worked out the equations of planetary motion in our solar system. And what this satellite did was it spent about 4 years staring at one particular region of the sky in the constellation of Cygnus the Swan. So just off of the plane of our galaxy. This is the Milky Way coming through here in the lower left. And there are just a whole bunch of stars in this field of view. And you need to look at a bunch of stars because you need a very fortuitous alignment of the planet's orbit around the star. So even if there was a planet there, but it was tilted, if its orbital inclination was tilted by enough, you wouldn't see this effect. So you need to look at a lot of stars to see the few of them where you get this particular architecture setup. And so Kepler was monitoring about 160,000 stars, and it discovered about 3,000 planets. And so this is, as of 2013, the planets that Kepler had discovered. Again, shown on the x-axis here is showing the orbital period, and on the y-axis is the size. Because remember what Kepler measures, because it measures how big the planet is compared to the star, because it measures how much light it blocks. What you see here is the size of the planet relative to Earth. So Earth would be down here at 1. Neptune would be here at 4 on the y-axis, and Jupiter would be here at about 11 or 12 on the y-axis. And so Kepler has discovered a bunch of planets, many of them between the size of the Earth and Neptune. If you wanted to find a true Earth analog, you would have to come out here to about an orbital period of 365 days with an Earth radius of 1 Earth radii. And Kepler really hasn't discovered an Earth-like planet in an Earth-like orbit around a sun-like star. But we have found lots of Earth-sized planets, and many of those planets are orbiting stars that are much lower mass, kind of like the Proxima Centauri star. And so they happen to be at distances such that they are in the habitable zone of their star. They wouldn't be in the habitable zone of the Earth, of the sun, but they would be in the habitable zone of the star they happen to orbit. And we now have going up another satellite called TESS, the Transiting Explorer Survey Satellite, that is discovering even more of these.
We have another question.
Sure.
Have we reached a point in measuring the radiation flux emitted from these planets to match the possible range of surface temperatures expected for habitable planets in a circumstellar habitable zone?
So, I mean, we have found planets that are too far away from their star so that they would not be getting enough radiant flux and they would be too cold. We have found planets that are too close to their star so that they would be getting too much radiant flux and they would be too hot. And we have found a few that are in that Goldilocks zone, in that habitable zone. And those are particularly interesting stars, planets to follow up. And I'll hopefully be able to talk a little bit more about that near the end of the talk today. So now we found lots of planets, and exoplanet science is now a kind of a full-fledged field on its own, and we're learning more and more about planets around other stars and habitability and stuff like that. But almost all of these planets have been discovered around stars that are similar to the sun in that they are main sequence stars. They are middle-aged, older stars. And it's actually hard to learn about how planets form when you're looking at planetary systems that are several billion years old, because all of the action that distinguishes, say, this core accretion from this gravitational instability, that all happens in the first few million years. So you really want to be able to look at very young stars in order to do that. But very young stars are very petulant, kind of like teenagers. They don't really want to do what they're told, and they cause lots of problems. And in particular, the big problem that these young stars cause is that they have very strong magnetic fields. So one of the things that I do in my career is I try to measure magnetic fields on stars and on young stars. And one of the things that magnetic fields does is cause spots. And so if you look at the sun, which is shown here in the upper left, it has sunspots. These sunspots are regions where there are very, very strong magnetic fields on the surface of the sun. So to give you kind of an idea, the typical magnetic field on the sort of the general part of the sun is on the order of about a Gauss, which is about the same strength as the magnetic field on the Earth that is interacting with your compass. But in a sunspot, those magnetic fields are about 3,000 Gauss, so 3,000 times stronger than the general rest of the sun. And because the magnetic fields are so strong, it leads to a number of effects that produces these sunspots. Well, young stars, and this is an image that was created by doing an analysis of the time variations on a young star. We now know that these young stars have huge spots on them, much, much bigger than anything you ever see on the sun. And so what do these huge spots do? Well, that's shown kind of in this animation. You see in the top here, a star rotating, and a really big spot rotates around and through the field of view. And here in the bottom right is a single spectral line blown up in great detail. And when there's no spot on the star, that spectral line is symmetric but broad. And that's because part of the star is rotating towards you. And so that part of the star is blue shifted. Part of the star is rotating away from you, and that part of the star is red shifted. And the spectral line is coming from all parts of the star. And so the spectral line just appears as something that's very, very broad. But when the spot comes through, it is effectively blocking some of the light from wherever it happens to be. And so when it's on the blue side of the star, when it's coming towards you, it causes a distortion in the spectral line on the blue side that's just there. And then as it moves through, that distortion moves to the red side of the line profile. And that's actually what allows us to map these, to make maps like this. But when we're doing these radial velocity measurements and we're not looking at the star at really tremendously high spectral resolution, what we're trying to do is just measure the center of the spectral line. And if we don't know that there's a spot there, we would measure the center of the spectral line, kind of where my little laser pointer is pointing here. But when that spot comes through, it distorts the shape of it, and it becomes hard to define what the center of the spectral line is. And it really just causes problems for our measurements. And it turns out it also makes the star get dimmer when the spot comes through. So this method, the existence of these spots causes problems for both the radial velocity method, and it causes problems for the transit method. So it makes it very hard to find planets around heavily spotted stars. But there are ways to potentially get around it. And one of those ways is to look at the stars at different wavelengths of light. A spot looks dark, not because it's not emitting any light, just because it's emitting less light than the surrounding star is. And that's because the spot has a different temperature. So on the sun, the general part of the sun's surface is about 6,000 degrees, and the spot is about 3,000 degrees. And on these young stars that we study, the general temperature of the star is about 4,000 degrees, and the spots are maybe 3,000 or 2,500 degrees. And so that means in the optical part of the spectrum, the spot looks very, very dim. But as you go to longer and longer wavelengths, the way the light is emitted, the spot becomes less and less dim relative to the rest of the star. And so that means this distortion that you're seeing move through the spectral line becomes less and less significant when you look at longer and longer wavelengths of light. So that's what my team and I did. We looked at young stars, we looked at optical wavelengths of light, and we also looked at infrared wavelengths of light. And here you see all the data from one of the stars that we've been monitoring. And it's noisy. It's noisy in the same way that the Proxima Centauri B observation was. But you see kind of a regular repeating of a signal. But the key aspect of that is that the amplitude of that signal is the same in the optical part of the spectrum as it is in the infrared part of the spectrum. And a star spot wouldn't do that. A star spot would have the optical signal 4 or 5 or 6 times stronger than the infrared. So this was a candidate planet around a young star that we discovered back in 2016, and we published it as a candidate. We weren't sure about it prior to this publication. No planets around stars. So the star we were observing is only about 2 million years old. It's called CI Tau. And so prior to that, no planets had been discovered around a star this young. And so we didn't want to say, absolutely, we have found a planet, because when you claim something very unique and very new, people will work really, really, really hard to prove you wrong. And so we wanted to cover our bets and say, well, it's a candidate. We think there's a planet around there. But we were pretty sure, and we wanted to try and verify that. And so what we did was we continued to analyze our data more and more carefully. And the main thing that we were trying to look for is that these measurements I'm showing you, these radial velocity measurements, are the radial velocity of the star. But when we take a spectrum with our ground-based telescope of the star, if there is a planet going around the star, the planet is is being seen by our telescope too, because the planet and the star are really, really close together on the sky. You can't resolve them. They're too close together. And so if there's any light coming from the planet, we are getting light from the planet into our telescope at the same time that we are getting light from the star. And if the planet has spectral lines, and you would expect that it does, because, for example, Jupiter has methane in its atmosphere, and so methane produces spectral lines in the infrared. If there are any spectral lines from the planet, they will be in the spectrum that we're seeing too. But because the star is moving in a very small circle around the center of mass, but the planet is moving in a very large circle around the center of mass with the same period as the star, that means the planet has to be moving much, much more rapidly. It's moving very fast. And to give you a sense of what that does, so shown here on the right is as a diagram of what different wavelengths of light going along the x direction would look like as a function of time going on the y-axis here. And the star's spectral lines are shown in black. And at the scale that I've made this plot, because it's showing a lot of wavelength range, the star's spectral lines are moving by such a small amount that you can't really even see it. But the planet's spectral lines are moving a lot. They're the things shown in white. So every time the planet goes around the star, its spectral lines move back and forth a lot, simply because it is moving very, very fast. And so,
we have another question if you have.
Sure, go ahead.
What about dust knots of greater density within accretion disk? Could they not produce similar profiles using these methods that can be mistaken as false confirmation of planetary candidates?
Well, so in principle they could, but the planets, the stars we're looking at, the disks around them are tilted at a particular angle to us, so the disk is not between the star and our line of sight, and the disk itself is relatively cold, but the planet, when it forms, just for the same reasons that stars get heated up when you compress all that material together to form a star, planets also get heated up when you compress all the material down to form a planet like Jupiter. And this planet, I should say, I didn't mention, this planet was about, based on these measurements, was about 8 or 9 times the mass of Jupiter. So it's a pretty massive planet. So you do have to worry about that, but also, oops, going back, the disk is symmetric around the star. So it isn't really producing something that would wobble one way or another, whereas the planet is all concentrated in one place. And so as it goes around, it actually produces a particular wobble in a particular direction. So it's a good question. There's things to worry about there, but there are ways to sort of take that into account. So what we wanted to do was look for a signature of this planet going around, these spectral lines of the planet. Now, again, the planet is much fainter than the star. The planet is maybe 500 to 1,000 times fainter than the star. So seeing an individual spectral line is really difficult. And if you were looking at one observation, you'd be taking one slice through this. And the white lines would just be very, very weak compared to the black lines. However, if you've taken a whole bunch of spectra, and we took a whole bunch of spectra to create this, if you knew how the star is moving, the planet is moving in just the mirror image of what the star is doing, and the only thing that you don't know is what is the amplitude of it. So if the star is moving up, kind of here in the middle, the planet has to be moving down in the middle at exactly the same time the star is going up. And so if you have very weak lines shown here in the bottom of the planet, it will appear at one wavelength at one observation, another wavelength at another observation, another wavelength at another observation, and maybe another wavelength at another observation. But if you know how it's moving because you've mapped how the star is moving, you can say, well, okay, maybe the planet is moving 5 times the velocity of the star, but in the opposite direction. Or maybe the planet is moving 10 times the velocity of the star, but in the opposite direction. You can start to shift all of these spectral lines so that they line up with each other if you get the velocity right, and try and amplify your signal. And then what we do is we also use what is called a cross-correlation technique. Oops, why is this not? There's supposed to be an animation going on here, but it's maybe, no. Well, my animation's not working. I don't know why that's not working. The cross correlation just allows you to take what you think should be there, you multiply it by what is there, and you add it all up, and you get a peak in a cross correlation signal if you get everything lined up and it's all present. So we had our original observations of this particular planet candidate, CI Tau. We dedicated many more resources to get more and more infrared light because the infrared spectra, because the planet would be bright at infrared wavelengths of light. So we did observations at the McDonald Observatory 2.7 meter telescope. We did observations at the Discovery Channel telescope, which is a Lowell Observatory telescope that was funded primarily by the Discovery Channel. It's a 4.3 meter telescope outside of Flagstaff. And we took many more observations. And we did this this cross correlation analysis, and that's what is shown in this upper left diagram, which was that first thing I showed you on the second slide. And the white peak here is where everything gets shifted. We take into account all the shifts. So shown on the y-axis is, do we shift it by, everyone by a certain amount, or do we shift it by a greater amount, or an even greater amount, or an even greater amount? And when we shift it by the right amount, we get this white peak showing up, which is a peak in the cross correlation function that I was trying to show you, that indicates we have actually detected the spectrum of the planet going around this star. So, and we detected at a very statistically significant level. The first thing it does is it confirms the planet is really there. We detected it at exactly the amplitude we expected it to be there. And the really interesting thing about this particular star is it's only 2 million years old. And so if the core accretion idea of how planets form is correct, and it takes 10 million years to form a planet, well, this planet exists in a system that's only 2 million years old. And so we now have very good evidence that that this planet formed through this gravitational instability method. So this is actually one of the first times we've been able to say just exactly how a planet formed. All those planets that Kepler discovered, the 51 Pegasus planet that I talked about earlier, the first one that was discovered, we knew there were planets there, but we weren't really able to say anything about exactly how they formed. And this is one of the first pieces of evidence that tells you kind of how a specific planet formed. And it almost certainly formed through this gravitational instability method. So we've been looking for other candidates. We've actually been using the Kepler satellite to look for other candidates that might show something like this. And we've been getting more radial velocity observations of them. This is coming from the Gemini telescope, Gemini South, so down in Chile. These are the radial velocities for that particular planet with an orbital fit to it. And we've been finding additional examples of this now, again, around very, very young stars. And so it suggests that planet formation actually can occur very, very quickly, that it's a very, very robust process. And that taken together with what we do know about extrasolar planets indicate that that there are indeed lots of planets out there. In fact, our best estimate now is that every star out there has at least one planet around it, and many of them have multiple planets. And so the next thing that is coming up is a new series of telescopes, the James Webb Space Telescope, to be launched in hopefully 2021. The European Extremely Large Telescope, a ground-based telescope, it's about 30 meters in diameter, in 2024. The Giant Magellan Telescope may be commissioned in 2021. They're working on it now. And the 30-meter telescope, hopefully coming online around 2022, though its construction has been delayed due to protests in Hawaii, so not quite sure when that's going to come online. These telescopes are all being specifically designed in order to measure the atmospheres, to take spectra of the atmospheres of planets that we discover around other stars, nearby stars, including planets in the habitable zone around their nearby stars, these nearby stars, in order to try and figure out what the chemical composition of these planets are, and to then look for signs of life on those planets. So kind of the holy grail in this whole field is to look for, or to try and find, an inhabited planet. It's a tall order, primarily because even though we might be able to use these telescopes to say, yes, that has an oxygen atmosphere, or it has a methane atmosphere, or it has ozone in its atmosphere, to be able to conclusively prove that the chemicals that we find in the atmosphere of these planets come from a biologic process, from a life process, is going to be probably the primary challenge. So I certainly think within the next decade, we will know what the chemical composition of planets around other stars is from telescopes like this. It will still be difficult to be absolutely positive that we have found life on a planet outside of our solar system. But that is certainly the goal, and that is the direction the field is going. And the work that that my group and I are doing are trying to understand how we get to these planets in the first place. And we're starting to now really test the various models of planet formation to figure out which of the ways that people have imagined are the ways, in fact, these planets will form. So I'm getting near the end of my time. I think I will stop there, and thank you again for inviting me to speak to you, and I'll be happy to answer any additional questions anybody might have.
What is your current research project?
Well, so this is an ongoing project. I mentioned some of these other candidates that we found. I have a couple of graduate students working with me. One of them is working primarily on the finding of planets in the first place, so doing the observations to look for the movement of these young stars and to make sure that we're not being fooled by spots or disks or anything else. And then I have another student who's working very much on this type of analysis to actually try and tease out the signal of the planet spectrum itself in the spectrum that we collect from the stars. And again, that's quite a challenge because the planets are anywhere from 500 to 5,000 times fainter than the star that they happen to be orbiting. So it's just a very difficult process to tease out that very weak signal.
Okay, I don't see any additional questions. I'm going to go ahead and switch back to Doug.
Okay.
All right. Well, thank you very much for that very interesting talk. That was great. Thank you for doing that for us and for being our main speaker tonight. Next up, we have David Haviland with a member's minute on recent lunar images.
All right. Good. Show a couple of images that, nothing. I've got a few images I'd like to run by you. It's been a interesting few months. There's been some times where we've had absolutely, whether it's DSO or lunar work, not much in the way of compliant weather. But unfortunately for me, most of it has been out at 4 in the morning, because for some reason the waning side seems to be the clearer side instead of the waxing side. I honestly would prefer the waxing side. So this is a shot around 4:30 in the morning, and up here the CG11 with the camera that I've mentioned mostly, the QHY 175. QHY5 178M monochrome, and I'm working it all through fire capture. This one is off of Marinick Terrace, off on the southwestern side. What really got me was the detail around the craters and the multiple split center spur peaks here in the crater Theophilus. This is prime. This is with just the camera. In the C11, no Barlows are used in, I don't think, any of the ensuing shots. The central area is between Sorrentiatus and Imbrium. It's up on more on the north side with the mountain range in here with Exodus and Aristotle's. This one was particularly a challenge for me. This is the crater Poseidonus. You can see the floor fractured crater, as well as a secondary crater on the inside. And you can see some of the rills coming down. This is a particular interest area of mine because this is where Apollo 17 landed, but this is in a rough area. You can see that the terminator is over here. This is about the best I was able to do. You only get about a 2-day window for this area because it's very highly reflective. And if you can't catch it early because it's in the dark, and if you catch it too late, it's completely blown out. But I was able to zoom in on the Taurus Littrow range, and I've just realized this asterisk is misplaced. It needs to be about over here where the arrow is. But you can see these mountains all around on all 3 sides. The South Massif and the North Massif mountains are almost 1.5 miles high, and they had to take Challenger this way, flip it over, and do a pinpoint landing right there. It's pretty awesome. One thing that also caught my eye, and I'll mention this throughout a couple more slides, is this crater called Dawes. It doesn't have the traditional fractured walls, and I'll show that shortly. Going off to the southeast, down around Nectaris again, I've got Piccolamini and this Rupus Altai. How this came to be geologically, I have no idea, but the whole detail in the area was just absolutely fascinating, with the change in the color and with the detail in the craters. An old favorite, back to Tranquility, Ritter, Sabine. Come on, mouse. There we go. We've got Aldrin, Collins, and Armstrong. These craters are only about 2.1 miles wide. Collins is. We've got Sabine C, Cat's Paw, an 11 landed here just off of Mulkey. I can really tell the seeing if I can't pick out these 3 craters. If I can't pick out these 3 craters, the seeing is terrible. This is over processed, and I will admit this is over on the Imbrium side. This is the crater Plato. This is a mountain Mont Piton, and I've got a higher up on it next. But as far as over processing and images, I don't know about Doug, Trevor, and Chris, but I'll process an image and stick it in a computer folder and leave it for a day. And if I like it a day or 2 later, then I'll think about putting it out on the net. More often than not, I delete it and start over again. And many of the images that I finally do put out have usually had 1 or at least two restarts. This particular one is that mountain, Mount Piton. This is with a 2.5x Barlow. This is 1.5 miles high, some 3 or 4 miles across, and about 8 miles wide this way. This is one of the Astronomical League objects on the moon they want you to try to find. I need to try to work this up just a little bit better. This is over on the western side, Aristarchus and Schroeder's Valley. Again, I want, like that one crater on the other slide, I want you to take note of this one. These are straight, not straight wall, but they're angled. These walls have not collapsed on these craters. And it's particularly interesting because then if you go to something somewhat larger, like Copernicus, the walls here have completely collapsed and have actually started filling in part of the floor as well. This particular one was taken back in July. This one is a fascinating one. This is a crater Schiller. I just dropped the gentleman's name, Barringer, the guy who owns who tried to mine and like the family foundation still owns Barringer Meteor Crater in Winslow, Arizona. When he was back in his day trying to figure things out, he found meteors coming in with as low as a 30-degree angle would still produce a round crater. This is clearly not a round crater. This is a glancing blow. All this stuff over here is where whatever came in hit, scraped, and left all of its behinds here, and then shot off. This is a glancing blow. Now, the interesting thing about Schiller is that it's 43 miles apart at its widest, 108 miles long, and it's 2.3 miles deep. You don't see much in the way of the collapsed walls. These walls are pretty rigid and pretty solid. This is a fascinating object on the southern end. And then down near the south area, I got the big three. Tycho, which I love this crater. I can get lost in it. Magnus, which is good. One of my real all-time favorite is down here is Clavius. I'm working on trying to get a single shot of Clavius, and I think that's pretty much the theory of crater formation, and that's it for me. Back to you, Doug.
Okay, before Doug comes on, we had one more question for Dr. Johns-Krull.
Okay.
Here we go. The question is, any comments on red dwarf stars supposedly being hostile to life due to radiation emanating from them?
So that's a very good question, and it's a question that a lot of people are working on now, including some of us in the physics and astronomy department at Rice. There's an ongoing NSF-sponsored project to understand that better. And the real issue is that red dwarfs are, they're cooler than the sun. They emit less light, and so their habitable zones are much closer to the star than in the case of the sun. But red dwarfs in general are kind of like those petulant young stars I was talking about. They have generally strong magnetic fields, and one of the things that the magnetic fields produce is flares. So the sun has flares, solar flares. Solar flares can cause problems for the Earth. It sends out storms, solar storms that can interact with the Earth's magnetic field and produce geomagnetic storms that can knock out power lines, that can damage communication satellites and so forth. And these red dwarf stars do that also. And because their habitable zones are so much closer to the star than in the case of the sun, any flare that goes off from a red dwarf would be a bigger effect on a planet that happened to be in the habitable zone of one of those stars. And so people worry about the radiation environment that may be present on one of these red dwarf stars, a planet around one of these red dwarfs. So, radiation can be harsh. It leads to mutations. At the same time, it's probably not a deal breaker for life, but it may be a deal breaker for the evolution of higher life forms, just because you have to have more go right to get a more complicated creature like a human. So, it is something that is actively investigated now. I don't think it's going to stop the ability for life to be there, but it may well affect the type of life that could evolve there.
Thank you. David.
Yes.
We had a question for you. Is
okay.
is this a regular SCT C11 or the Edge HD C11?
No, this is
Great
the original CGE CGE 11. It's got the bright star optics, but it's not one of the new the really super new ones.
Okay, thank you. Okay, back to you, Doug.
All righty. Thank you, David, for those recent lunar images. And David, I just have to say that your lunar imaging, I don't know if you see it yourself, but has improved immensely over the last year. So it's incredible what you've been able to accomplish. Okay, next up, DIY astronomy. This is one of mine, remote control of radio telescope using Raspberry Pi. So the purpose of these DIY astronomies are to show things that we can do as amateurs that may be interesting. And last month I showed you a radio telescope that I made for, here's a picture of it, for less than about $150. And the configuration I showed you last month was hooked up directly to a laptop computer. And this month I'm going to show you how I've been able to hook up to a Raspberry Pi and control this system remotely. So this radio telescope, it's made out of just a Wi-Fi antenna, and it's set up to measure 21 centimeter or 1.42 gigahertz hydrogen emission. This has to do with the hydrogen atom and the electron flipping from one state to another. When it does that, it emits this 21 centimeter radiation and allows us to be able to detect hydrogen clouds in our galaxy. So the way this works or looks is above this is the antenna, and right after the antenna, there's a low noise amplifier with a hydrogen bandpass at 1420 megahertz or 1.42 gigahertz bandpass. It gives us about 40 dB of gain. And then below that is the software-defined radio, the SDR receiver, and then I have this SDR receiver hooked up to a Raspberry Pi. So it's the same as what I showed you last month, except that I now have the Raspberry Pi instead of a laptop. And I want to do this so I can control this whole system remotely. Okay, so similar to what we've been doing with other configurations, a lot of people in our club and others have been doing this thing where we want to use a Raspberry Pi or other microcomputer to be able to control our telescopes and our cameras for astrophotography, so we don't sit out in the backyard all night long with our laptops, and our laptops get wet with dew and all this stuff. Instead, we will put a Raspberry Pi or other small computer out with the telescope and be able to control it remotely, with a laptop in our house or some remote location. So in this case, when you're using a Raspberry Pi like this, the Raspberry Pi is operating as a driver server. So when we use it for astrophotography, it operates as a driver server too. You hook up your cameras and your telescope mounts and all this. And in that case, we've been using software like K-Stars and ECOS. But in this case, for using it for a radio telescope, the software is called Spy Server. It's the same principle, it's still operating as a driver server, but now we're using the software called Spy Server, which I'll show in a second. And on our laptop, instead of running K-Stars as we do when we're doing astrophotography, now we're running a client application called SDR Sharp, and there's a plugin called IF Average plugin. So the Raspberry Pi is outside with the radio telescope in the weather, and laptops inside a nice air-conditioned house where you don't have to sit out there in the weather with it. And the other thing is the difference in cost. Raspberry Pi costs about $35. My laptop costs a whole lot more than that, and I'm a lot more comfortable leaving the Raspberry Pi out in the backyard for days and days than I am my laptop. All right, and they're connected by my house's Wi-Fi. So on the driver server side, this is what it looks like. This is Ubuntu or Ubuntu, however you want to pronounce this operating system, running on the Raspberry Pi, and you just pull up a terminal window, and all you have to do, once you've loaded the Spy Server software, you just run two commands. The first one shown here is a run command to turn on the bias T, and a bias T is just supplying DC power to the low noise amplifier. So what this means is the SDR, the software defined radio, is actually going to power that low noise amplifier I showed you. but you just run this one command. It's going to put out 5 volts to run that, so you don't have to run a separate power supply for it. Then you run this other command to start the SPY server right here, and that's all there is to it. Just these 2 commands, and they will start. They will communicate to the software-defined radio and the low noise amplifier and run the whole thing and allow you to connect to it remotely, just with those 2 commands. Then on the client side, the application, this is SDR Sharp application running on a laptop. Over here on the right, you have your spectrum. This is what the is coming in real time. It'll show you each spectrum coming in. These are gathered many times a second. Then on the left-hand side, this is the IF average window. So just like we do in astrophotography, where we stack a whole lot of images together to create one better image with lower noise image, better dynamic range, lower noise, all the better things by stacking many images together, I'm doing the same thing with this. We have all these spectrums coming in here in real time. If you look at this number down here, we're actually stacking together, adding together 902,000 spectrums, and then those are being displayed over here. This is the average of 902,000 spectrums being displayed over here on this side. So the noise level is much lower. So you can see it's minus 70 dB. We're over here on the spectrum. This is minus 55 dB. So you gained quite a lot, 15 dB or so in noise by averaging all these spectrums together.
Hey, Doug, question. Yeah. Where are the best online resources to download and play with these software tools?
Oh, I'm going to show you that on my last slide. So let me get to my last slide and I'll show that to you, because, you know, like I told you last month, I would just love to tell you that I figured this all out by myself, but I didn't. Okay, I saw someone else had done this and I copied their whole thing that they did. So I'll show you at the end how to do it. All right, next. Okay, so if you do this, there is a problem. When I hooked it up directly to the laptop, I didn't have too much of a problem. But when I started using the Raspberry Pi, I had a 6-foot cable originally going between the software-defined radio and the Raspberry Pi. And I had significant noise problems. Over here on the left-hand side, you see all these spikes. And I, looked at this for days and tried all kinds of settings and stuff. And I could not figure out what in the world was going on. I was getting a little, frustrated with this whole mess. And it dawned on me, in my experience, in the end, when I figure out the problem to something, it's always something that actually made sense. And I don't know why I didn't think of it originally. All I did was take out the 6-foot USB cable between the Raspberry Pi, and I just hooked up the Raspberry Pi directly to the software-defined radio with no cable, like I showed you in my picture. In fact, I'll back up just to make sure you know what I'm talking about. See, right here, here's the Raspberry Pi, here's the software-defined radio, no cable. I just hooked the USB connection between these right together, no cable, and that gave me a significant improvement in noise over here. You can see the huge difference between these two. So if you do this, just be careful about what the cables will do to you. Well, for whatever reason, it was not a problem when I was using the laptop. I used the same cable, no big deal. But when I used the Raspberry Pi, whatever, I had all kinds of noise issues with that cable. Okay, so if you were with us last month, this is a video that's very similar to what I showed you last month, and I'm going to show you the results of this configuration. Now there's 2 things. On the right hand side, this is stellarium, and stellarium is going to go through a 112-hour day, and you're going to see the Milky Way cross it twice. There's going to be the summertime Milky Way is going to cross it, and then the wintertime Milky Way is going to cross it. The antenna is pointed right here in the middle. It's pointed straight up, right at the zenith, and that's what we're actually going to be measuring over here. So I'm going to run it once, and we're going to look at stellarium. Okay, so here comes the summer Milky Way, and it crosses. Here's the antenna right there. Okay, that's the summer Milky Way crossing it. And then here comes the winter Milky Way. Okay, and that's crossing it. And then when it gets done, there's the sun down there. This is going to be over a 24-hour day. So now we're going to look at the spectrum over here. When the summer Milky Way crosses it, you're going to see this blip come up here. You see it's shifting to the red. It's red shifted, shifting to lower frequencies. When the winter Milky Way comes through, you're going to see a blue shift comes out here this way. So the winter Milky Way is actually coming towards us, and at 30 degrees declination. The the winter Milky Way actually at 30 degrees is actually coming towards us and it's blue shifted. But at 30 degrees declination, when you look at it, you actually see a red shift with the Milky Way actually is moving away from us. And if I'm confusing you about summer and winter Milky Way, what I mean is the summer Milky Way is the one we see in the summertime, like the one that rises up above Sagittarius. And the winter is the one we see in the wintertime, the one that runs down Cassiopeia and Canis Major and that side of the Milky Way. So that's the resulting video and spectrum from at 30 degrees declination. Now, these are some plots that show different declinations. This is 30 degrees declination, 30D. This is 20 degrees. This is 10 degrees. This is 0 degrees declination. This is minus 10 degrees declination. This is minus 20 degrees declination. And what's interesting about this, okay, the blue one, the blue is the winter Milky Way, and the red one is the summer Milky Way. So with these different declinations, you can actually clearly see it red shifted for some areas that are an indication of that part of the Milky Way is moving towards us. In other areas, you can see it's clearly blue shifted. Like this winter Milky Way is definitely, towards blue shifted and more towards higher frequencies than is the summer Milky Way at that declination. Now, interestingly, when you start looking at, as I started going farther and farther towards them, this is actually near the point at the middle of our galaxy. Actually, I'm starting to see a red shift in the winter Milky Way. And I haven't quite figured that out, but I'm just trying to get this to work right now. And then the summer Milky Way, because I'm pointing directly at the middle of the galaxy or near the middle of the galaxy, we're not seeing much of a shift anywhere. And I probably should have told you the normal frequency we're looking at is 1420.4 is the non-shifted hydrogen frequency, 1420.4. So right in there is where we would see the hydrogen if it was not shifted one way or the other. Okay, so now there's something else interesting that happened here. Okay, I'm going to run this video again. You're going to notice that right when this thing goes by, where is it? Deneb. Okay, I missed it, sorry. Right when this thing goes by Deneb and the Northern Cross or Cygnus, we actually see this interesting spike over here. I'm going to run it one more time so we can see that. All right, I'm having trouble seeing it. Where is it? Okay, there's Deneb right here. See this spike right there? That spike is occurring right when the telescope is pointing right at the radio telescope is pointing right at the Cygnus loop or the Veil Nebula. So I looked this up, and the Veil Nebula is a known radio source, and I saw this this actually occurred several times, and it appears that this spike here may be actually that we're picking up something from the supernova remnant, the Cygnus loop. And I'm going to look into that, see if I'm going crazy or not. But this actually lasted for several samples, and once it was past this point, it disappeared. And in case you're not familiar with what the Cygnus loop is, the Cygnus loop is a supernova remnant. It's also called the Veil Nebula. There's a western veil and an eastern veil. The NGC 6960 is the Witch's Broom down here, and NGC 6995 is the Waterfall Nebula, also called the Network Nebula up here. But this whole thing is a supernova remnant, and it's pretty easy to believe that this is a supernova remnant. You can see things, it looks like things are blasting out from the middle of this. This is a picture I took of the Cygnus loop at the Eldorado star party a few weeks ago, and this shows you what this particular what the radio telescope was pointing at right there when it picked up this blip. So that's kind of convincing that we may have picked up something from a supernova remnant, but we're going to look into that more to see if we are crazy or if that's really true or not. Okay, so to answer the question, how did I do this? There's a link here I'm sharing here. This shows you the link to the source of the design. This tells you where to buy all the equipment, how much it cost. It tells you how to set up all the software, how to do the video I just did with Stellarium there, and it's really great. I've posted my presentation from last month on my webpage, which is www.holland-observatory.net. You can go there, and the same link is there that you can click on, and you can go and see the design information about this radio telescope. But so www.holland-observatory.net, or you can try to contact me if you can't find this. But this is really a fun DIY astronomy project. And to me, if I can go out in my backyard and set up something for less than about $150, and if I can measure the hydrogen moving in our Milky Way, I think that's pretty cool. So I'm pretty excited about doing this, and maybe the rest of you would like to do that too. So that's the end of my talk. All right. So next up, we have a members minute with Chris Wells on recent images from Eldorado Star Party. Take it away, Chris.
Chris, you have a go.
Thank you, Doug. Thank you, Trevor. Okay, this first image is an image of happiness. I think this is me actually on a vacation at the Eldorado Star Party. Like many others, I've been just working from home and very, very closeted over many, many months, over the last 6-7 months, and actually to get out to West Texas, my favorite place, I think, in the world so far, with your own telescope equipment and start imaging again is fantastic. So this is an image of equipment and happiness about actually getting away from home and doing what I love, which is imaging. There were actually 5 of us from the Johnson Space Center Astronomical Society that attended the Eldorado Star Party in West Texas. So I thought it only fitting that I show you the first 5 astro images of many that I took during a period of 6 nights. You see on the left and the right there, I've given you screen captures really of my hard drive of the sort of content and the massive accumulation of photons that I collected during that period. Lots and lots, 20 plus astro images, many of them yet to process, but I have got through the first 5. Okay, the first image, something that I've always wanted to do is a wide field image of the North American Nebula. I took this with a refractor. It was actually a Takahashi Sky 90 operating with a reducer at f4.5 and just a DLSR camera. And, beautiful emission nebula. And you can see here, there's just a great outline there of kind of the Gulf of Mexico region there. No hurricanes right there. Beautiful, and it's all just lovely colors. I actually really delighted to be able to actually take that photograph. I've never taken that before. I've always done it with a sort of a narrow field of view image or equipment, but this time I've managed to do that. I'm not going to talk about any red shifting or blue shifting. You've heard about all that in previous presentations. So, any picture of America with reds and blues on is probably not something to stay clear of right now. Next image, Iris Nebula. This is a very different set of equipment. One of the things I really wanted to do when I went to West Texas this time was to take a very deep image. I think this is probably the deepest image I managed to accumulate. I took this with a C11 with a hyperstar setup on it, which took it to a very, very fast optical train of f2. Focal ratio of f2 makes it very, very fast at capturing photons. It's actually with a cooled camera, this one. It's actually an ADIC camera, a cooled camera, and has about an 80% quantum efficiency. So you're really looking at staring in space for a period of 3 hours using f2 with very, very high sensitive equipment. And I just love this, reflection nebula, the blue at the center of the iris there, and all the black dark nebula that's sort of shielding the stars from behind it. Next image is in Cygnus, of course, the Crescent Nebula. What I was pleased about with this image, with the same equipment, the same fast optics, and the same sensitive camera, was the fact that not did I just get the crescent, is that when you look around this image, you see more and more nebulosity, more and more emission nebula throughout the image there, particularly on the right there and down the side there you see lots and lots of nebulosity there just shining. It's almost like the whole field of view was red in some kind of capacity. Emission nebula just everywhere there. My only wish is that I could have gone wider than that and see what's out to the right, what's out to the left, what's above and what's below. Here's another very red emission nebula. This is IC410. A lot of people call this the tadpoles, or the tadpoles of IC410. You can actually see sort of the tadpoles here illustrated right down here, the tadpole images. Once again, nice image, a little bit softer. This was actually taken on the following night from the preceding images. This was actually on Tuesday night, and I think conditions were just a little bit softer there. But nonetheless, it was an image I was pleased with. This was 24 images, 5-minute sub-exposures, all stacked and processed together. And the last image was something very different, something that I hadn't really done before. This is taking what I call an ultra-wide picture. One of the things that I did was I borrowed just a simple Ioptron SkyGuider Pro tracking mount from Treavor, who's going to tell you about the star party a bit later on. So I borrowed his mount and I put my just my 55mm lens on a Canon DLSR, and I pointed at the same area of space for approximately 2 hours, taking 2-minute sub-exposures and stacking them after. This is an area called the Scutum star cloud. This is actually a really awesome object visually. You can see it naked eye, not from home, not from light pollution central in League City, but you can see it in West Texas. And you just look up there and you see just nebulosity everywhere, just stars everywhere. M11, which is called the wild duck cluster, is actually right in the center of there. Because it's such a wide field image, you can't really resolve the stars. But that's M11. That's and once again, this is the Scutum star cloud area. Visual object, absolutely lovely to pick up just with a simple DLSR camera. And thanks to Treavor for the loan of his SkyGuider Pro mount to do that. That's a testament to the mount, actually, when you think that I didn't touch this equipment. I just left it taking pictures for the period of 2 hours, and it hardly moved in those 2 hours to be able to accumulate that shot. So that's it. That's my first 5 of many, many more to come images. I hope you like it. And back to you, Doug.
Hey, Chris, hold on a second. David had a question for you. He was asking about the black stuff in front of the stars and back, like the horse head, where the dark stuff is in front of the background stars. I'm assuming that's coming from your iris photo.
Right. Let's go back to the iris photo. Yeah. So this is all dark clouds of dust, really, in front of stars that are behind. So we call that dark nebula.
All right. Thanks, Chris. Back to you, Doug.
Okay, Chris, thanks for sharing your pictures with us, and we're looking forward to seeing your other ones. And yeah, we had a great time at the Eldorado Star Party. I would invite everybody else to consider coming out there. It's just a lot of fun, and we had 5 people from JSCAS there, and Trevor's going to tell you more about that in a minute. All right, next up we have David with Star Party News. Tell us about David.
David, you have a go.
All right. Yeah, Chris, I was really impressed with how much dark matter there was, if that's the correct term, in that picture, because it seemed like the more I looked, the more there was of it. So that one really got me. Okay, Star Party News. This is going to be very brief. 12th through 17th, we have the Eldorado Star Party. We're hearing about that now. We're going to hear a little bit more about that from Treavor. On Friday, October 23rd, we had the All Clubs meeting. Oops, not at HMNS, but this was done virtually with Robert Reeves in San Antonio. For those of you that missed it, feel free to take a quick snapshot of the screen. It's on HAS's YouTube, and he was more than happy to let it be posted. Go back and hear the entire meeting, and it was an exceptional meeting. On Friday, November 27th, yes, the day after Thanksgiving, we actually have our last Hack Wine Star Party of 2020. Very likely it's going to happen. It's going to be a waning moon, so the moon's probably not going to be a factor because it rises at 9:16. It's going to take at least an hour before it clears that building and another half hour before it clears the tree. So this is going to be a DSO night. I planned it that way. I also planned it pre-COVID, so we'll just have to make the best of it. Hopefully, Orion and Mars and a few other bright things will be out. There is hope. Hack is asking for 6 events for next year. We're going to start working up those dates. And social distancing is still the order of the day, so we're good with that for the time being. And at this point, I'm going to hand it over to Treavor for more details about the Eldorado Star Party.
Thanks, David. All right, so I've been to our local star parties. I've gone out to McCavitt once, but I really wasn't in it to try and do any imaging. I just wanted to do some visual observations at that point, but this time I went after imaging. So go through a couple of slides here for you. We're now westbound and down. Here's the truck all loaded up. Chris and I put everything together and we went in one vehicle. So thank you, Chris, for doing all the driving. So where is Eldorado Star Party? Well, it's that blip way out there in West Texas, 400 miles away from us in the Houston and Clear Lake area. Here's a picture of us getting some stuff set up and kind of a general field at that point. Here's another picture waiting for the sun to go down, getting ready to start some imaging out on the field. Here is a view from the lodge, which is about half a mile from the field. So this is where they host all the dinners and lunches and breakfasts, if you choose to get those. So we had a showing from Team JSCAS. Here's me next to my rig, and then by my tent and inside the tent. My wife was questioning whether I had ever been camping before, so I had to show proof that yes, I can do this. Here's a picture of Doug and with his setup, and then more getting set up, and Doug needed some space there. We had Brandon as well. It's him with his Dob, and then him with his Newtonian imaging setup, and just general conversations with the rest of the group. Here's Chris. I think you saw the one photo on his presentation, but all the gear. Chris, I think, won with the most pieces of gear out there on the field from our group. We had a fifth member, Al. He was up on the other field, so we don't really have any pictures of him, but he was definitely out there, and I'm sure he had a great time. Here's us having some fun in the sun, waiting for the sun to go down. Here's the tumblers that I put together for the guys. Al also has one. They're all to commemorate the event. And then a couple of the other presentations were talking about the Raspberry Pi. And so I wanted to know, did anybody order Pi? Well, yes, we did. Here it is strapped to the tripod. I have a supplementary storage attached to it as well. Here's our router that we took out in the field. So we had the Pis hardwired to the router, and then we used our laptops to remote over wireless into the Pis to do all our imaging process. One mistake I made about camping is I went off and left my jacket at home, so I had to put on 4 shirts because the temps started dropping and the wind picked up pretty good. And here's my Red Cat with DSLR, and this is sitting on Chris's Ioptron mount. So we basically traded mounts. He used his camera on mine, and I used my rig on his, so it all worked out. Here's what we're calling Team Pi. This is me and Chris. This image that Doug took of us in the middle of doing imaging. This is a video I put together where I had taken, this is the second night of imaging for me. And what this is a video of the Pi and K-stars and Indy all in operation. So I'm going to go ahead and kind of narrate this as it goes through. So what I'm doing here is one image session has finished. So I'm going to start to pick a new target. And what I'm going to do is I'm going to go and open up a FITS file from the previous night because I want the mount to go to that image, to that position in the sky. In this case, I just finished up some M31, I believe, and now I'm going to go back and shoot some M45. And so I'm navigating to the folder where the FITS files are. There's the M45 folder. And then I'm going to pick the last one. Just pick the last one because it was the last one. And just a second, we'll get back to the K-stars screen. Okay, and what I've told that to do is to move the telescope to that position based on that previous night's file. So just a second, I'll tell it to go, and it's doing a plate solve. It's going to come back and tell you it's way out of position at the moment. And now walk over and show you that the scope is now slewing to the new position. There it goes moving. And it's now approximately pointed back at M45. And the plate solve is going to continue through its process. Yeah, now it's capturing an image now of where the telescope is pointed at currently. And if you see that crosshairs in just a minute, there's there's M45 showing up. It's not quite where I wanted it positioned. Of course, the system is aware of that because it's going to try and get this centered the way I wanted it. And this is all based on that previous FITS file that it took from the previous night. So I'm not having to tell it to do anything. It's doing it based on that previous image. And another little bit here, you'll see that it's taking another image, and you'll see that that image will now shift to where it's more centered the way I wanted it. You see my, now it's centered the way I wanted it. So, you know, this is going to be the second night of taking images of the same target. And I now have that target is within 2 seconds of where it was the previous night. Now I'm happy with that. I'm going to go ahead and switch over to the imaging portion of the software. Sorry about the movements. I'm trying to do two things: hold the camera steady with one hand and move the mouse with the other. I'm going to rename it to match the file folder from previous, which was M45. And then I'm going to come up here and tell it I want to take 24 images at 5 minutes each. Okay, now you can see it. I've got the 25 images, and I'm going to add that to the sequence. And then I'm going to run the sequence, and at that point, it's going to start imaging for me, and I can basically walk away from it at that point. So you can see it's actually starting to count down, and then it's time to move on to the next slide here. Here's just a still of another target being imaged, and this is M8 and M20. Very wide field view from that red cat scope of mine. Why do we do all of this? So we can get images like this. And thank you. Until next time, I'm going to turn it back over to Doug.
Okay, Trevor, thank you very much. That was a very interesting presentation, and Trevor has really done a lot with this Raspberry Pi work that many of us have been interested in. That plate solving by using a previously taken image, that's incredible. I haven't done that yet. Congratulations on all the good success you had at Eldorado, and I hope you come again next year. That was fun being out there. Okay, so that's it for our meeting tonight. Our next meeting will be on December 11th, and our main speaker will be David Haviland, who's going to tell us about carrier cleaning and collimation of a reflector telescope. Hope to see you there. Thank you.